So English we make this title lah. The puzzle of deliveries. Can you find the best route? Okay. So when we talk about finding the best routes, it fall into a few problems lah. So one of it that we want to solve that related to our hackathon title actually is this vehicle routing problem. Okay, right. Or in short, we call it VRP. Okay, right. So you can just call me Go lah, Dr. Go. So I'm from University of Tunku Abdul Rahman. And well, let's see what you can we can learn together lah from today's workshop. Okay, right. So let me continue. Now, let's understand first why we need routing. Actually, we need routing every day. Okay, right? So basically, when we talk about routing, we are talking about how to find the best path, okay, from one to another. Okay, example in our daily life lah, like every day you're going to school. Okay, if you take public vehicle, then you have no choice lah. Okay, usually the bus will just go one path. Okay, right. So if you are on your parents' car, then your parents sometimes will use this path, sometimes will use other path. Sometimes they make the decision to use another path. If you are taking a motorcycle to school, sometimes you use this path, sometimes you use another path. If you are bicycle to school, then yeah, sometimes you may change path. So when you are changing some path, actually, that actually involves something called routing, because you are making decision to change your route, and to your knowledge, you think this should be the best. Okay, right. Now, even happen to the Grab, okay, Grab and Food Panda, now very famous, right? Now secondary school student also like to order Grab already. Okay, right. So Grab also same thing. So they also make decision because they need to find the best path, the so-called the most time efficient path, right? Because if they go a long path, then they may not deliver the food on time. So customer may complain. So that is also routing. Okay, right. They also need routing. So when we surf internet, okay, of course, we just get the data lah. But background behind actually is about how the packet should route. Okay, because network actually is a group of links. So how they go through different links, and then to make sure that the message or your information reach to you in the shortest time, right? So that even come to warehouse automation. Okay, warehouse even for automation, parcel delivery. All right. Let's say in the warehouse, how they put those parcel, okay, or put it nicely. So when the customer, how they can take it down. Okay, for those sorting warehouse, like now we buy things from Lazada, Shopee, right? The warehouse actually is very messy. So where should go where? Actually, those warehouse usually they centralize all the parcel, and they need to segment it nicely. Okay, this should go where, that should go where. So that is they're talking about routing. Okay, all right. And then when you play games, okay, especially when you play those 王者, Mobile Legend, or last time called Dota 2 also. Okay, right. So you have the NPC, right? So the NPC will, or maybe the computer lah, the AI. Okay, right. So they will know where you go. Okay, then they'll find they'll compute the shortest path to reach you. Okay, so that to hit you. So that also routing. That's why routing has been in many applications lah. Okay, all right. So then what exactly is routing? Actually, when we talk about routing, means it's a process of finding the best path. Okay, that you want to move something, okay, from one to another. Okay, so but in broader view, we are not talking about routing just to find a path. We are talking about the best possibility that match your goal. Now, most of the time we talk about shortest, but uh, as you go deep, you know that in routing, you know that shortest may not mean the best. Okay, so you still need to match back with your goal. Your goal is still more important. Your goal sometimes may not be shortest. Your goal may be other things like fastest time. Okay, especially in traffic, the shortest route may not be the best, or the shortest road may not be the best because maybe heavily congested. You may go slightly longer, but you can reach even faster. All right. So that's why I say shortest may not be the best sometimes. Okay. Now you may even go for lowest cost. Okay. All right. So time usually is money lah. Okay. The faster you deliver your thing, that means you get better reward. Okay. But sometimes actually is you go shortest route because due to a lot of these obstacles. So actually, it may not be cost effective. Okay, right. Now, sometimes short path, okay, for example, sometimes in especially in KL, big city like these Penang, Johor, Ipoh, right? It's a you see sometimes it's a straight route, but that path got 8 traffic lights. Okay, if you go a bit bigger route, only 2 traffic lights. Okay, right. So that may make you even faster to arrive. Okay. Now sometimes we also look into energy. Okay, all right. So this one may not be the vehicle case lah. Okay, but right now we talk about solar car or electric car. So lowest energy. Sometimes congestion will drain more energy. So better you go bigger route lah, or more smoother route. Okay. So in terms of network, we are talking about the same thing. If you use mobile devices, right? So sometimes the shortest path may not be, or it may be draining a lot of this power. Okay, maybe longer path should be better. So we need to see the scenario. We need to match your goal, and we want to find the best possibility. Okay, that process is called routing. Okay, can get that? All right. Now in Chinese, okay, there are many English easy lah. We just call routing lah. But in Chinese, you may have slightly different wording or terminologies lah. That actually because of the different field. If you apply in technical field like computer networking, usually we use the word 路由, okay, right, networking lah. If you use for AI, usually they may not use 路由, they may use 路径, okay, all right, for algorithm AI. For logistic, usually they use 路线, okay, right. In layman term, we use something called 道路, okay, 或者是公路, okay, all right. In some transportation or circuits, they call it 线路, okay. So for signal, sometimes they call 通道, okay, right? So you see slightly in a different field, they will use slightly different terminologies lah. But anyway, all this is associating with back to this what we want to discuss today called routing. Okay, yeah, all right. Okay, now when do we need routing? Okay, right. Now if today you at your home, you cycle to school, okay, you have only one path, no other path. That means A direct to B. Only one. Okay. No other path. Okay. So you do not need to even think. You just cycle only. Okay. Yeah, only one path. So this one, we don't really need routing because you have no choice. You don't need to make any decision. So it's not our interest today. Okay. Right. Now let's talk about second case. If we have A, let's say from your home, you need to cycle to a bridge. Then when you reach the bridge, then only you go to your school. Okay, so you go from A, B, C. You go from your home, you cycle to the bridge, you cross the bridge, and then you go to the school. Okay, right. That one also we are not interested because it's still one path, although A, B, C. Okay, so you still no need to think. You have no choice. So again, this is not our interest today. Now, even you have A, B, C, D, E, it's still one all in one in one path. That is not our interest today. Okay, right. So what we are interested is this case. If today you are at home, you need to cycle to a bridge. You cross the bridge, then you reach your school, which is A, B, and D. You may have another path where you cycle to a garden. Then from the garden, you go another route to the D. You go from the A to C to D. Now, this is our interest because you have you need to make a decision. All right. Which one is shortest? Which one is fastest? Which one actually save you more energy? Okay, because obviously you see here is A, B to D actually is a direct line or more straight line. And then you go to the C, you need to go through a curve or it will be slightly longer. All right. But again, it doesn't mean that A, B, D is the best. Sometimes A, C, D could be the best. But sometimes A, B, D is the best because it's a straight line. So we need to make a decision here. Okay. That is fall into our today discussion called routing. Okay, yeah? All right. So when we involve routing, usually you will see, okay, a few terms lah that you need to familiarize yourself lah. Right. The first, these terms we call nodes, or sometimes we call points. And later we call points. So point means this one, the A, B, C, D, E, F, G. This one we call, later we call points. So you want to be more technical, we call nodes. Okay, you got how many nodes? Or even more technical, we call this is vertex. Okay, all right. Or we call it many nodes, we call it vertices. All right. Then A to B, usually you have a path. Okay, so we call this is edge, or sometimes we call it link. Okay, all right. Then you always have a starting point. Okay, the starting point we call a source. Okay, source, and then your so-called your target. Okay, we give it a name called destination. Let's say you want to go A to F, so your A will be your start, your F will be your target, or you call your A is the source, your F is the destination. Okay, clear? All right. Then in the middle, other than links, sometimes you may use path. Okay, all right. Now link usually is more point to point. Path usually is maybe this C, F, you call this is a path. Okay, path. Okay, all right. You can call it end to end, also can. Okay, right. We use the word path. Then you may have another term called hook. Hook means you go through how many points? Like A to F. The shortest hook is 1, 2. Okay, or B to F also can. Then if you go A, B, D, E, F, then you go through 1 hop, 2 hop, 3 hop, 4 hops. Okay, so we use hops sometimes. Now, all the links, we have something called uh, price. Okay, how much price you have to pay. So we use another term called cost. Okay, now this cost may not be money, sometimes may not be money. So it can be representing some general, representing is a general term that we use to represent some effort, or maybe some, you can call it money, or you may call it some thing that you have to pay in order to use this route, okay, or this link. Okay, we call it cost. This is a general term lah. So if you want to be specific, sometimes we use distance, especially come to logistics, we use distance. Okay, and you may use weight when come to AI, or maybe networking, we use something called weight, right? That means how heavy. Okay, you want to use this link. So those are the some basic terminologies lah, that you may need to aware. Sorry, when come to these uh, so-called these the routing lah, when come to the routing. Okay, right. So student, until here, okay? Yeah, right. So let's go to something deeper. Now today I'll talk about three. In my part one, I still have three parts. Okay, part one, part two, and part three. Okay, so let's talk about the first part. Okay, now we continue from this example. Okay, this example. So you have how many? You have how many nodes? You have 1, 2, 3, 4, 5, 6, 7. Okay, you have 7 nodes. So let me change my pointer to a pen. Okay, now assuming that now you are from A. You're from A, from A, source A. You're going to destination B, can go to C, can go to D, can go to E, can go to F, can go to G. You're not going back to A lah, no point. Okay, right. So from B, so A to B, your next hop should be B, direct, am I right? Should be B, right? If you talk about minimum hop, should be B. But if you are considering the cost, so now each link I give a cost, okay? So cost. So if you want to look for the minimum cost path, or we use the word shortest path, okay? So A directly to B may not be the best because it's going to take cost of 12. Okay, mean bigger number, not good lah. Smaller number, better. So you will start to look for other path. You will look for maybe I try C first, then I go D, I go B. Not good. That one also very costly. So until you find actually A to C to B is the smallest cost. We use the smaller cost in total. So in that case, I'll use only 5. 3 plus 2, 5. So in that case, that A to B, so the smallest path, the minimum cost is 5, where the next immediate hop actually is C. Okay, can see that? Okay, now if I want to A to C, should be direct already. So seems C is only one path, okay, which is the smallest, A to C. So if I want to go to A to D, D is where? D is here. Okay, so should I use A, B, D or A, C, B, D? or ACD or ACFED. You have many choices. So you compute all the possibility. You will notice that actually ACBD is a smaller cost because 3 plus 2 plus 6, you get 11. So this should be the shortest path. You want to go from A. Okay, yeah? Right, let's continue for E. Okay, so you compute, so you get this outcome lah. So A to C to B to D to E will be 13, smallest. If I want to go to F, actually is A to C, the F is the smallest. If I want to go to G, A, C to G, then will be smallest. Can get this concept? Can get, ah? Okay, good. So now I want the the source, okay, or the starting point is from B. Okay? Okay, now I have the sample here. I need you to verify. I give you 2 minutes. Okay, faster, faster you verify. 2 minutes. Okay, can get? Okay, correct. Hopefully my calculation is correct. Okay, right. So you see from B, if you go direct to A, that's not the best. Okay, so you should go to C, then go to A, right? Then if B to C, of course, direct, is the best. So B go to D. Okay, so this will be the best. Okay, then B go to E. Okay, so B, D to E. If B go to F, direct is the best. If go to G is B, go to the C, then go to G is the best. Okay, all right. So let's continue. We need to find all out. Okay, now, oh sorry, I need to change my pointer back. Okay, right. Now we continue from let the source to be the C. Okay, so I already give you the calculation Right. So again, C to C, no need calculate Okay, like A to A, B to B, C to C, no need. Okay. Now we want to calculate from C to A, C to B, C to D, C to E, C to F, C to G. Okay. Now I give you 5 minutes. You try your very best to calculate all the shortest path out. Okay. Later I have another slide. Let you to cross check, see whether you get the idea or not. Okay. Right. Do it now. 5 minutes. Okay, right. There's a request from the organizer. So student, please sign in. You can check your this chat box. There's a sign in link. So please click the link and sign in. Right. Okay. So have you done? You managed to use paper and pen to calculate all the shortest path out. Or you already start to use AI already. Use your phone, capture down the screen, send to AI. Please calculate the remaining. I hope you're not doing that, all right. Because I mean, if you're taking part in the hackathon, I mean, you should learn all these concepts, lah. Okay, done. Okay, give one more minute, one more last minute. Okay, now let you see the answer. Okay, so this is what I calculated, lah. You can cross check, okay? If there's a wrong one, you can type in the chat box, okay? Maybe particular point I count wrongly. Okay, yeah? All right. Now, when you deal with, okay, later we'll talk about VRP, okay? The vehicle routing problem. Now, before we come to VRP, there are two concepts that I need to let you to know first before we move to that. Okay, so the very first thing is you need to at least must know how to calculate this kind of shortest path tables, all right? Or shortest path these are routing. Okay, this is the basic that you have to aware. Okay, can all right. I hope you get this correct, this concept correct. Okay, now let's move further. Yeah, all right. Student, if you need more time, just let me know. All right. Okay, now, so how do we get the algorithm behind this? Okay, so we define actually the distance, or maybe you can use the so-called the cost also cannot be used distance here So if you want to go from uh A to B, or I represent as I to J means your so-called source to destination. Okay, I is your source, J is to destination. Example. Okay, so if you going back to your own means you go from A to A, that means cost will be zero because you are at your own place So if you are not seeing a direct edge or direct link, you make it as infinity first. For example, A, I want to go to K. It's not there, not in the map, so should be infinity Okay. Now even at the start, let's say A, you want to go to F. If your immediate so-called nodes don't have, you make it as infinity first. Then you try to find the neighbors, okay, the neighboring node. From the neighboring node, you go one more layer, then you go one more layer until you find your targeted node, also called your destination. Then you compare these two costs from your initial, okay, let's say initially you don't see it, you put infinity. After that, you manage to go through a few hops and you see it, maybe the cost is 15. 15 infinity, which one smaller? 15 will be smaller. Then you try another route. Hey, you notice that this one I can get 10. So my previous best actually is 15. Then I get 10. So now I update with 10. Then I further find. Oh, I find 10 and 12. Actually, 12 is bigger than 10. No point to update. Then I continue to find. Okay, until I find 8. Oh, okay, 8 actually is smaller than 10. Then I update. So until you try all the possibility, then you manage to get it. Okay, then you update and you keep it. Okay, for each of these. You do for all of these. That means you try all the possible links without missing. So this method we call brute force. Brute force. Okay. So you try everyone. So the good thing about brute force, you can find optimum. When I say optimum means this is the best already. Cannot be anymore. Okay. Right? Cannot be anymore. Huh? Alright. So this is the good thing, also called the beauty of using brute force. Of course, the bad thing is you take you much longer time definitely much longer time. Okay, right. So by doing this, actually you are simplifying the problem from this problem. All right. So you see, imagine I have a truck. I need to go to a destination. So I don't know how to route. Okay, right. So but you have a table, okay, that clearly to guide this guy if you want to go from A to B, where you should go, how you should go. Then if you want to go for B to D, how you should go. From let's say F to G, how you should go. So actually you are actually okay sorting the best path for this vehicle. Okay, right. So in our daily life, actually is I believe you use a lot Google Map and Waze. This is actually what they're doing. They always find the smallest cost path lah. Of course, their cost is actually time, smallest time, or so that you can reach your destination faster. Or of course, they based on we call ETA lah, estimated time arrival lah, right? Because sometimes traffic very hard to predict. They also do estimation, but based on what they estimate, they give you the minimum or so-called the shortest path that from your target to your destination. Okay, right? Clear this concept? Okay, now this is in the routing category. We call this is one to one. Okay, that means you are go from A to D or A to E or maybe B to F, G to B. Okay, so it's one to one. Okay, right. Now this is the basic that we need to know first. Okay, now I will guide you another second part of my this workshop. Okay, now your scenario now like this. Okay, so you are starting from this point. Okay, all right. And sorry, my mouse got some problem. Let me clear this and throw again. Okay, so you're starting from this point, and you need to visit not only one point, you need to visit several points. For example, you need to visit this node, this node, this node, this node, this node. And you may require to come back to your original point. So how you should go around the path? Should I go this first? Go here, go here, go here, go here, go here, go here, go here. How? There are too many possibility. Or you can derive this as a permutation problem. Okay, right. So when you come to this problem, so the minimum or the shortest path algorithm that you learn may not be sufficient. You need to go a bit more to enhance from that. Okay, so let me show you how we usually solve this problem. So this problem we call it as TSP. Okay, traveling salesman problem. So this is like you are a salesman. So your boss, okay, needs you to go to this maybe 5 to 6 location in a day to maybe clear all the sales, or maybe to collect back all the the payment or something like that lah, or maybe collect paychecks. So you need to plan in the way that how can I complete this task in a day in this particular given time. So and you need to somehow plan in the way that you don't want. I mean, first of all, you must collect back all the point. You cannot say I go this 4.1. I go tomorrow. Cannot. Okay. Okay, not efficient. Cannot. So you must collect all the point. You must visit all the point at least one. You may visit more, but at least one you must reach there. Okay, that's a condition. So you are struggling from here and how to make it. Okay, this is actually the path that I want towards the end. So this one we call traveling salesman problem, or we call TSP lah. Don't make it as STP. Sometimes people may say as salesman traveling problem lah, can lah. But actually STP in computer networking, we have another thing. We call it spanning tree protocol lah. It means another term. Okay. So the short form that we use is called TSP. Okay, TSP, not STP. Okay, TSP. Right, let's see. So for TSP, the condition is you must visit each location at least once. Maybe twice, it's fine, but at least once. Okay, right. So usually we need to return back from your original point. Okay, so where you start, you should come back to that point lah. Okay, unless under special case lah. Okay, you may say that okay, I finish all the route, then I complete my task. Okay, that's my goal. Can also lah. Depend how you derive lah. But usually you may need to come back. Okay, now sometimes you may need to come back. Depends your problem that you want to solve. Okay, right. And again, we need to hit minimum total cost. Minimum total cost. Okay, total All right. So that's why you need to stack on what you learned previously, the minimum, so-called the shortest path to continue to hit. Okay, now, if you're dealing with a few nodes, or in this case, let's say we talk about traveling salesman, so we talk about cities, okay, or how many points. If you talk about 4 points, uh, you actually very easy lah. You have only three possibility, or three possible routes. Okay. Now it can go complicated if you need to visit more points. Example, if you need to visit 10 points, so you will have 100,000 plus of possible routes. Okay, which will be the minimum. Very, very headache. Okay, not easy, not easy. So how do we calculate actually how many possible routes? There's a formula lah. We use this formula n minus 1 bracket, then exclamation mark, or so-called factorial lah, divide by 2. Okay, you know what I do is because your start and your end are the same. I assume that we are dealing with the case that you need to come back to your original point. Okay, so the start and the end are the same. Okay, that means you need to come back. So it will be n minus 1 exclamation mark by 2. Okay, now if I put 4, let's say 4, how do I get 3? 4 minus 1, you get 3. 3 factorial is 3 times 2 times 1 is 6. 6 you divide by 2, you get 3. So that's how you get 3. If you have 10, 10 minus 1 is 9. 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 divide by 2. That's why you get more than 1,000. Okay, more than 100,000 plus. Okay, so I have a table to show you lah. If you have 4 points, 3 possible routes. You have 5 points, 12. You have 6, you have 60. You have 7, you have 360. You have 8, you have 2,000 plus. 9, you have 20,000. Wow, scary, yeah. 10, you have 181 plus. Your hackathon problem, you got how many cities you need to visit? Easily 40, close to 50, right? 48, right? 50. 50 minus 149 factorial divided by 2. You can calculate. Okay. So you cannot use brute force. Okay. Cannot use brute force. Okay. You cannot calculate all the possible. You can say I throw to AI. The AI may run for months. Okay. Now, you have this complication to solve already. Okay. Yeah. Right. And oh, sorry, I just read the question. What is factorial? Okay. Okay. Factorial. Okay, let me type something in the chat box lah. When you have example lah, if you talk about 3 factorial, you need to make it as 3, wait, 3 times 2 times 1. Okay, Okay, I type in chat box. So if you talk about 5 factorial, so you need to make it as 5 times 4 times 3 times 2 times 1. Okay, Right, so this one we call it factorial. Okay, N is for quantify, right? No. N, okay, in my context here, N actually is a general. We talk about anything can be N number. You can represent everything into this correct. Usually we go the other way around, like easy lah. Okay. Can also 1 times 2 times 3 times 4 times 5 also can but usually we do a bit reverse lah. 5 times 4 times 3. To make sure we don't miss anything lah. Okay, now when we talk about these so-called n, okay, the n can be anything, because anything you can make it as any representation. If you talk algebra, anything can be algebra, and you can represent anything into A, anything B, everything as C, D. Fine. So n is just a representation of something lah. Okay. Now this number right now in our case we call it the points, or the cities that you need to visit. We put n. So if you need to visit 4 cities or 4 points, then at the end, how many possible routes or how many possible links? No, it's like should be any possible path that you need to go through. Later I have an example to show you. Okay. So what I want to bring you here actually is, if the number of cities you need to visit is large, then you need to calculate a super huge large number of possible, all the possible path, so that from there only you can see which is the best minimum or the most optimum one. Okay, if you want a very, very good answer. So that actually relying on how many computational power that you have. Okay, in hackathon, you have 50. Okay, you have 5, 0. Okay, minus 1 is equals to 49. Okay, factorial. Divide by 2. Okay, all right. Okay. Now let's see further. I'll give you an example first. I don't want to scare you. Okay. Now, let's say I use a brute force way. Just now we talked about 4 points, right? Let's say this is the topology that I give to you. This topology. Yeah. Right. So you have A, B, C, D. Okay. Right. So you all are considered linked. Okay. And I make sure all is linked. And each of the link I make an assumption. Let's say they have this cos. A to C is cos 2, C to D cos 4, B to D is cos 3, A to B is 6, A to D is 1, B to C, C to B or B to C is 4. Okay, now let's form all the possible routes out first. Okay, now you can go A to B, then to C to D. Then after that, come back to A. You can go A to B to D to C, then come back to A. You can go to A to C to B to D, then come back to A. Only three. Only three. Hey, you can say that I can go from A to C to D to B, but it's the same lah. So because in our case is A to B and B to A is the same. Okay, we make this assumption first lah. Most of the time we'll make this assumption, but there are some case example uh you especially in KL. So when you go to this particular destination, you use this route. When you come back, you are forced to use another route because too many one way, too many single path. Okay, all right. So in that case, your course A to B and B back to A is different already, But in our context, we make it the same first. Okay, yeah. All right. So if you are taking consideration of all the costs, so you calculate A to B is 6, then 6 plus 4 is 10, 10 plus another 4 is 14, plus another 1, 15. So you calculate each of the costs, you notice that actually if I want the best route for this TSP problem, my route should be A to C to B to D, then back to A. This is the best, and you can say that this is also the optimum one because we already scan through all the possibility. This is the best. Can? Yeah. All right. Now let me go further. Okay. Now, the formula we use is very easy. We just need to total up all the costs, okay, that here total up A to C, C to B, B to D, D to A. Okay, I total up all the costs. Okay, right. And what I do actually is you can see here, I just sum from here to here. Okay, so it's just a breakdown So I just sum, okay, distance from let's say A to B, B to C, C to D to yeah. In our case here, actually is A to C, C to B, B to D, D to A. All right. So this is the just example to show you. Okay, now then if your topic go larger, actually you can plot. Okay, after you know this is for formula, you can safely put them into a table like this. Okay, so easy for you to figure out, okay, if you have large topology, how are you going to get the best path? Okay, right. So there are a few ways, and not only limit to these four, mainly today I talk about these four. Okay, so brute force, just now we have discovered that we try all the possibility, we try everything. This one you will get, sorry, my pointer always go a bit. Okay, so this one actually is we try all the possibility. So from there, actually we get the best path. Okay, this is optimum. Okay, very good, very good. Okay, just that it take long time. Okay, now dynamic programming actually is later we're going to discuss. We're going to use this. Okay, why is because brute force we're going to give you too much time to get. Okay, all right. So we may try to use a smarter way. Use DP. DP also can achieve optimum. Also can be the best. Okay, right. Now if you want fast, you have to do guessing. Fast okay, right? So we may use greedy algorithm. Greedy is very fast, but it not guarantee optimum. It not be the best. It somehow is good, but it may not be the best. Okay, so if you want somewhere around balance, okay, may not guess too much, but also may not use too much time to get the optimum. Somewhere balance heuristic is the best. Okay, they are somewhere in the middle of these dynamic programming and greedy. Right? So we'll go through all these So So in that case, if you ask me which is the best, I will say depends the situation. Okay, so like what I mentioned just now, brute force is good. It give you okay. The first thing we need definitely accuracy is the best. We need to make sure accurate. Now, bear in mind, all these four algorithms will ensure that all nodes are visited. Just that whether they are the best or not. Okay, brute force guarantee the best. Okay, but again, very slow because you need to check all the possibility out. Okay, direct programming, yes, also give the best. Okay, in terms of speed, slightly better, slightly improve. Okay, all right. So greedy is very fast. Among these four, the fast one. Very fast give you answer already. But it may not be optimum. If you are lucky, you may get optimum, but sometimes it may not be optimum. Okay. Now we go somewhere in the medium. Right. The speed not too slow, not too fast, just nice. And I may not get perfect optimum. I may not be so bad, okay, like greedy, but somewhere acceptable lah. Or near, we call it near optimum lah. Okay, heuristic. Okay, right. So let's go through. Okay, like what I said just now, the example, so you remember this example, 7 cities. Okay, now, if my salesman start from A, I want to visit all the link, then come back. What is the minimum cost? You want to challenge before I release? Before I release the answer, we will discuss the answer. Okay, see whether you fast enough or not. I give you 2 minutes, 2 minutes. You see what is the best. Okay, we start from A, Okay, you need to come back. You first of all condition is a hackathon condition also you need to visit all the nodes you need to visit all the nodes, and you must come back. Okay, which is the minimum cost? Okay, you do first 2 minutes very fast. Then we discuss. Okay, Mr. Yo got answer already. Very fast Cost 33. Wow. Okay, later we check Later we check Okay, now. Okay. For this one, like what I say, if you want to be uh okay, all right. Later we discuss. Oh, sorry. Later we discuss. This one very interesting. Sorry. Okay. Okay, this question very interesting. Okay, there are actually three path, three solution. Okay, right. So we usually see one only Right. Let's discuss this. Now, for this case, it's 7 cities. Can we use brute force? Because brute force guarantee give me optimum. Okay, right. Now this is brute force. You can use brute force, but like what I say, you have 7 cities minus 1, 6 factorial, divide by 2, you get 320 divided by 2, you have 360 possible routes. You need to list all these routes like this. Okay. Then only you need to calculate each cost and find the smallest one. Okay. This is one way you do lah. But again, this is going to take you too much time. Okay. All right. Of course, you can filter out, I want only A, okay? I don't want from G, okay? All right, you can simply, but I mean, if you move out, you have to scan all because you don't know. Okay, let's do a better way I suggest you for this kind of question, you can use DP. Again, under DP, still got many sub different algorithms lah. So the one that I use is something like a Bellman algorithm. We call it Hellcat. These algorithms. Okay, right. So let's see this. Let's see this. Okay, right. Right. Okay. Now, just now we have calculated. So you remember this table? Just now we have calculated all the shortest path from one to another location. So for the step one under this DP, we based on, let's say from A, my assessment from A. So I will see this part which is the minimum. C lor. Okay, so we will go to the C first. Okay, of course, under DP, you will still calculate all the possibility again. But since we have this table, we'll try to utilize this table. Okay, right. So we'll go to the C first. This is the step one. So I managed to link one city already. Then I will link the second city. Okay, so I will calculate from C to B is how. So AC to example, D is how, AC to E how, AC to F how, AC to G how, and then maybe even A, B to C how, okay, maybe reverse is better. So it calculate all. So I should illustrate to you two example only lah, huh? Let's say if I want to link, I'm talking about link, okay, I want to link C and B, should I go A, C, B or A, B, C? So in this case, you see that ACB cost is 5 and ABC cost is 14. Definitely ACB is better. Okay? Right. So up to this stage, your goal is to link two city. Okay, yeah. So either ABC or ACB or ACD or ACF, ACG, whatever lah. You try your best. And after you list out, then you choose the smallest one. Okay, in this case, very obvious. Is ACB. Okay, so I managed to link two cities already. Now I link three cities. So I go further. So I should link A, C, B, D or A, B, C, D or A, maybe A, E, D, C. Okay, I don't care. As long as three cities are linked, not including the A, three cities. So from this example, if you via B, so you get 5 plus 6, 11. So if you via C, you'll get 14 plus 8 equals to 22. If you try direct, you may get another path. Okay, anyway, so after your calculation, you get the best is 11. Actually, what you no need to recalculate one. Of course, computer will do this thing because you can always utilize. Like what I say, you can utilize back this table. That's why this table is very important. This is your first step. Once you have this table, you can just refer. Okay, now I already get A to C. Then I want to find C to B how. Then B to D is how. Okay, so you can easily tap, okay, by seeing the minimum cost. You try to link all these minimum cost. That is the fastest way lah. Okay, of course, computer here, it will just show you all the possibility. Okay, just as your knowledge lah. All right. So in this case, I managed to link three cities. So I'll further do this for the four cities. Okay, so four cities, I'll go from A, C, B, D, and E. So if I go further, five cities, okay, I will go from E to F. Okay, depends which part that you wire. After that, I'll get six cities. Okay, right. So is it solve all my goal? Actually, my goal already finished because, like what I say, I need to ensure all nodes visited or all points or all cities visited. So I managed to 1, 2, 3, 4, 5, 6 cities. My job done already. Okay. Second condition is you need to back to A. So I'm now at G. How should I go back to A? Okay, I can go to F, B, and come back to A, but this is not the best because it's too costly. So after you calculation, try all the possibilities from G back to A. Actually, if G, C, A is the cheapest cost. So in that case, you will go C via G via C, then back to A. Okay, right. So computer will calculate for you, but if you already have, if you just now do the first step, okay, you can use this table. You see G, okay, go to A, actually 7. Straight away you plus this figure, to recalculate lah. Yeah. Okay, so if you calculate from fresh, you will do like computer. You're going to check each city that you connect, you're going to check all the link again. But if you have pre-calculated just now the shortest path table, you can make use of that table, help you to faster to establish all the links together. Okay, so until here, actually, yes, again, Mr. You're correct. Okay, these are total shortest cost actually is 33. Okay, it is from A, C, B, D, E, F, G, and A. Okay, 33. Okay, now I want to highlight. Actually, there are still two more possibility. Okay, for this DSP problem, just now what I show you is we end our last point is G. Okay, now your last point can be B, can be also C. Okay, how Now if your end node is B, is easier. Reverse off. A, you go to C first, you go to G, then you go to F, you go to E, you go to D, you go to B. Okay, B is your last. Then after that, you come back. Okay, via C, you go to A. That also gives you cost 33. Also optimum. Okay, now how can I end at C leh? Hey? Interesting, ah? Okay, N and C. Anyone want to try? Just now what we did, okay, I repeat back my question. Just now, if we visit A, C, B, D, E, F, G, our last node actually is at G. Then only we return back to A. If you go reverse, you have A, then C, G, F, E, then D, then B. Your last node is B. Now there's another possibility is your last node is C. How ah? Okay, you circle. Anyone want to guess? Okay, I give you the answer lah. Okay, see two ways lah ha. You A actually, although you via C, but you don't visit C first. You just go through only. You visit B, then you visit D, you go through E, you go to F, you go to G, you come back to C, then only you come back to A. So your last node will be C. Or there's another possibility lah. Or you A, you direct go to G. You via C, yes, but you don't stop at C. Okay, but the link still count as 7 lah, okay, right? Then you go to F, go to E, go to D, go to B, go to C. C will be your last visited node. Only you go to A. Okay, so you pass through may not mean you visited. Okay, right. Now when I say visited, why? Because in hackathon, when you visited, you need to pick up the item. There's a parcel you need to pick up. When you reach the demand, so-called the customer side, the shops, you need to put down. That's called visited. Okay. But your case may be complicated because your lorry may have a certain, how to say, certain amount of rooms, I mean the items that you can pick up. Maybe you have space of maybe 100 units you can pick up. When you come to the farm, you have 200 you need to pick up. So you cannot pick up in one way. You need to pick up in 2 rounds. Okay, you have this complication. But here I'm talking about when you visit the link, you visit the city may not mean that you want to visit the city. Sometimes you pass by, Example, when you take a flight, you do a transit. Example, you want to fly to Japan. Okay, so you may fly to Hong Kong first, but you just wire only then only you go to Japan. You may not go down to Hong Kong, jalan-jalan, then go to go to Japan. All right. So you may pass by, okay, but you are not visited because you are not doing anything with them. Okay. All right. So in that case, how you get the ending can be C. Understand? Okay. In your hackathon, very important concept. Okay. Because in your hackathon, you need to pick up the item and you need to deliver the item when you reach. That is called visited. Can get Okay. Good. All right. So in short, actually under DP, okay, so we are talking about you reach the this city of J, means you try to reach the city. You try all the possibilities from your previous visited these cities, and you pick the cheapest or so-called the lowest cost path or link. Okay, so this is just the algorithm to illustrate to you lah. Then only you find the last answer here. Okay, now do we still have other method other than DP, okay, or maybe greedy heuristic, still got other problem lah. Now, I split this into two big category lah. When we deal with TSP, actually, we usually want guarantee. But again, when you use guarantee, you need to sacrifice a bit on the speed, okay, because you may need to calculate more. If you want fast, then you may not able to get optimum. But of course, we try to get near optimum. Okay, right. Now, if you want guarantee, I want the best, no matter how. I don't care what resources that I want to use. So other than brute force, dynamic programming, you can use branch and bound. You can use integer linear programming. This is also quite famous. You can use cutting plane. You can use branch and cut, and there are also others. Okay, that you can Google or you can use AI to suggest. Those are guaranteed optimum. But again, you need to have resources to calculate that. So if you want fast, okay, you may not want to, maybe you have only computer, may not have a good GPU, okay? Then you can use something faster lah. Greedy is very fast, but again, it may not guarantee the minimum. You can use heuristic, still got 2-op, 3-op, whatsoever. You can use GA, okay, genetic algorithm. You may use ACO and colony, optimization algorithm. You may use SA tabu or some randomized search, even some randomized, sorry, this one repeated, randomized search and also others, right? But those actually like going a bit greedy heuristic type, actually they are usually not optimum, or you may get near optimum. Of course, we try to push until near optimum lah. Of course, if you're lucky, you can get optimum lah. Okay, all right. So you have plenty options to me. Okay, right, to solve your hackathon problem. Okay, like so what we discussed actually just now was one to many. Means you have one salesman, you go to many town or many cities to deliver your items or to collect your items. Then you need to come back to you need to reach back your starting point. Okay, now let's come to our today highlights. Okay, VRP. Vehicle routing problem. When we talk about VRP means now I have many vehicles. Okay, I need to visit many points. So, but I have limited resources, or I may have limited vehicle. I may not have 10 vehicle. Okay, or I have vehicle, but I have my limitation. Maybe my vehicle can go too far, or my vehicle which is smaller is a van, not lorry. Okay, so all these are fall into VRP problem. So we try, in other words, we try to find the optimal routes for multiple vehicles visiting a set of location, or maybe a group of location, or maybe is various of location also can. All right. Now this is the sample that I showed to you. Okay, you usually have a starting point. We call it depot. Okay, right, or you call it start point. And this case, I have three lorries. I have the red lorry, green lorry, and blue lorry. So I have a few points that I put some number lah, and the route that particular lorry visited, so I highlight in color. Okay, so this is the one of the examples that a VRP problem. Okay, right, now become more challenging. So I use back this topology, which is complicated enough. So instead of just now we try 7 cities, now I have A to A here, B, C, D until I, J, K, L, M. I have 13 cities here. Complicated enough, cannot use brute force. Okay, right. Now, let's say I have three lorries. Whether should I use two lorries or three lorries to cover all the nodes? Then each links have a cost. This one not so easy, Mr. Yo. Okay, now, okay. So I want the answer is whether two lorries better or three lorries better. If you think three lorries is better, what is the total minimum cost? Okay, compared to the two. So I mean two lorry minimum cost is what? Three lorry minimum cost is what? Try to make it near optimum. Okay, I give you 2 minutes. Okay, before we discuss further this question. Okay, there's a question. Can I use starting point? Sorry, use multiple times. Can. Like what I say that each point you can via lah, huh? You can via. Okay. Again, just now we have discussed visited and via. You may visited, but you can pass by also. No issue. No issue. Huh? But usually you don't go back starting point lah, because you go back starting point means you return already. Your lorry come back already. But of course you can pass through. You can via also. No issue. Can. Okay. Yeah, very challenging, Okay, like. Okay, let's see how we solve this question. Okay, like this is really related to your this hackathon poll. Okay, now still got no more. Okay, right. Two lorry. Okay, let me see how okay, whether two or three lorry better lah. Okay, now let's see. Now for this question, definitely no brute force lah. It's also going to take long time. Can I use DP? Dynamic programming, that's just what we discussed for the PSP. Actually can, but again, it will take long time. Take long time because now your topology is almost double. From 7 cities now become 13 cities. Okay, so it's I'll say longer time lah. Not to say cannot. Usually DP will works well for small cases. Okay, it's better than brute force, but again the topology may not go so huge. Okay, under certain number of cities, then you're going to because your computation will go exponentially. I mean exponentially when it come to calculation. Okay, now for huge topology, because each route is a permutation. Okay, like what I say is a factorial. So in that case, we have to either use greedy or heuristic. Okay, now compare greedy and heuristic, which better? Just like I say that heuristic is balanced, greedy is fast, but comparing optimal, which will be better? Okay, let's discuss some possible examples here. Now, let's say I use greedy. Let me guide you how greedy works. Okay, starting from your depot just now, our question, this one, okay, right. So for your starting point, the red color one, we call it depot Right. So your immediate link is where? E3. Okay, your E, that's right. E. Then your I, 4. Direct link is 4, Then L2, H here, G, and C. C. F cannot, F is not direct, Okay, now, so from here, I start with greedy. I use two lorry first. Two vehicle, two vehicle. So the first vehicle definitely is L lor. I'm going to link the L. Okay, right. The other vehicle, I can choose to link H or link E. Can one, no problem, no problem. Okay. We just pick one. Let's say I link with here. Okay, right. Now I continue from L, greedy where I go to the smallest I will link with M. Ew, sorry, my okay, so I link with here. Okay, all right. So here I can choose either B link to B or link to F lah. All right. So if I link to B later, I link to F, then all higher cost because I link back cannot because you don't want to form back a loop form back a loop will be a trouble. So in that case, I may go. Let's say I link here first greedy. Let's say I choose this. Okay. You may try also if I link to B, what happen? Can also right. So here I continue. Also here definitely I'll go between 3 and 5 or 8. I definitely link this smaller one. Okay, right. So until here, I will link with this Okay, right. Till. Sorry, my. Yeah. Yeah. Never mind. I draw again. Sorry, I by accident I quit this. Okay, let's link this back. So I get this. I'll get this. I'll get this. Okay, so I'll get this. I'll get this, and I'll get this. Aye. Oh, come on. Okay, right. Okay, so from here, I will go greedy I'll go here. So here I go greedy, I'll go here. So from here, I'll go greedy, I go where? I go A. Okay, so from here, I go greedy, I will go here, cannot yet. I won't go E, E visited already. I won't also visited, so I go here. Okay, so here, no choice already Like you don't go back these two so I'm forced to go here. Okay, here job done. Okay, now I come back because I can go H but it's 8 Okay, may not be worth Okay, right, you can still go I can go H, then only I come back, can also. This will cover here and cover here, can also, okay, can also. If you think you want to go here, okay, then only go here, can. No, nothing wrong, possible. But whether is it the best, we don't know. We don't know, right? So, or maybe you don't want, you let the other side to cover, okay, because it could be quite far. Because this guy still got smaller one, okay? So I will continue to visit where? Visit this guy first, then visit this guy, then job done, then I go back. Okay, so here also I go back. I use the smallest cost to go back. Okay, this will be the two really using two vehicle. One of the example. You may have other example. then you need to try all the possibility under greedy, then you see the smallest one. Okay, all right. So let me show to you. This is what I calculated lah. So I managed to get 45. Of course, I need to stress greedy is fast, but doesn't guarantee optimum. You may come out another greedy, which is better than mine. Maybe you get 43. I don't know. Okay. All right. So like what I say, greedy will go. Okay, let's say E, F, B, C, A, D, then H, G. Okay, possible. It may go like what I say, it may go H first, then go G, then may go, let's say C, or may go D, then go something else. Possible, possible. So you try your best to calculate. I just show you one of the example that outcome of the greedy. You may have used greedy, it may have another slightly better optimum. But what I'll show you is you may get this one of the solution. Now compare 2 or 3. Now if I use greedy 3, what I will get? You will get something like this. Again, this is just one of the example. One of the example that you may get this. Okay, so quite obvious, all right, quite obvious. 2 vehicle total cost is better than 3. Am I right? 45 and 51. Okay, so definitely 45 better lah. Okay, why I need to spend extra 6 cost? Okay, just to capture all the routes. Okay, now why 3 vehicle may not be best is because you still need to calculate the comeback time. Okay, unless you no need to come back, maybe 3 vehicles is better, but you're required to come back to your depot, to your starting point. Then in that case, it may not be the best for this case. Okay, now but sometimes 3 vehicles could be better because you finish the task faster. Okay, so if you have time, here I don't put in the time, I only use the distance constant. So you may have time, okay, in that case, that it can finish faster. And if you have limited length, example, your lorry cannot go 200, for example, cannot go until 200 kilometer. You can only cover, example, 100, within the 100 kilometer. So in that case, you may need to use small lorries, break them into a smaller distance. In that case, more vehicles is better. Okay, but if you only okay talking about just a pure distance cost, so in that case, that for this case, if I use greedy, 45 is definitely better than 51. Okay, right. Can we get better? Just like I mentioned one more method called heuristic. Okay, now let's see heuristic. Okay, now, again, under heuristic, there are many sub-methods. Okay, so what the method is, I would suggest or come to this discussion is we'll use this so-called heuristic with heuristic with saving cost, something like that. Okay, right. So how do we do only 3 steps? You let the depot starting point to be not 0. Okay, so that's fine. Second is I will calculate using some algorithm. I may use Gistra or this for Washoff to obtain this minimum cost or the immediate cost lah. Once I have, then only I calculate the saving cost. Saving cost is let's say from A and B. What I do is I calculate the distance from depot to A, what is the shortest path, and then the distance from depot to B, what's the shortest path, and then between A and B, what's the shortest path. Okay, so that means I'll use the distance from depot to A cost plus the depot from B cost minus between A and B. So the bigger I save, that means the route is better. Okay, so this is step 3. So let's see step by step. Step 1, what I'll do is, like what I say, I will have starting point at 0, no issue. After that, I'll find all the immediate path. So I highlight all the immediate path already. We try with 2 vehicles first. All the immediate path. Okay, we draw it out. Fine. Then I continue. Okay, I expand. Let's say from E, I expand. I get these 2. Immediate you don't go until A. Okay, immediate. Okay, so C immediate is B lor. I don't go back to B lah because already covered by this guy. No point. Okay, so I won't go D because it will cover by other point because other point will use lesser cost. So you find all the, if this is tier 1, you find all the tier 2 that can be covered by tier 1 using the minimum cost. Okay, so you cover. So on the other side also, this will cover here, this will cover here, this will cover here. Correct? I use the, okay, when I want to go for tier 2, okay, or 2 hops, I use the 1 hops with the minimum. Okay, again, you can use some algorithm or what I mentioned now, huh? You can use this Gstruct, or you can use this Freud, this Warschaft, or others, okay, that can do this step for you. Okay, now, third part, how I do cost saving. Cost saving, okay, cost saving. Okay, how do I do? Okay, now the cost saving is using example I want to find example. I want to find A and B. Example A and B. Okay, so what is the minimum cost from A? I mean to A, minimum cost. You calculate. Let's say minimum cost A is 7 plus the minimum cost B 5 lor, huh? 5 Ew. Sorry Okay, minimum cost B is 5 example. So you get 12 lor, huh? 12. Okay, you need to minus between A and B. What's the cost? 4. So in that case, you get how many? You get 8 lor. Okay, so this is the idea lah, huh? This is the idea. So why we do this is because later we want to link, we want to put those biggest cost saving to link them, better put them into the same path. Okay, right. So we will start to come up something called cost saving table. Okay, so you do lor. A and A definitely is no lah. So A and B you get 8. Okay, like what I show you here lor. You get 8. So A and C again you do from depot to A the minimum cost, depot to C minimum cost, then you minus out the cost of A to C. Okay, so you get 8. So you do all out. Some don't have one some because too far away. Okay, no point. You put dash. So you calculate this out. Okay, now how you should link them? Let me guide you. Okay, so you start from the big number one. Example, I start with B and F. I link them because cost 9 I save a lot. That means you higher number here because it's saving You save 100 ringgit and you save 9 ringgit. Which one that you want? Definitely save 100 ringgit lah. Okay, right. So in that case, B and F you link them first. So you link here. B and F you link them. Okay, B and F you link them. Okay, now let's continue. So 9 no more, I go to the next biggest number. A and B. Okay, A and B, okay, link. Not you link, Okay, now you need to remember when you link, you don't want to create a loop. Create a loop, then your vehicle forever will be merry-go-round, cannot come back. Okay, all right. Then A and C, yes, you link them. Okay, so we have joined here, we have joined here, here, and here. Okay, right, let's continue. No more, then 7 don't have. Okay, now this A we don't join because A and C and C and A are the same. So this is redundant. Okay, discard. Okay, we continue. Okay, then we link by 6. Okay, so 6 D to C, C to D. C to D, don't join. Okay, fine. Then next one is E and F. Good, E and F we join. Okay. Then after that, we go further. Okay, another one, E and F already join. Okay, fine. Now, E and B, should we join or not? E and B, we cannot join because we join, you will create a loop. So cannot. So we don't join. It's a loop. So ignore. Then we continue until G and H, we join. Okay. So once you join, you calculate whether correct or not. I have I need to count 1, 2, 3, 4, 5, 6, 6 cities, 6 links. 1, 2, 3, 4, 5, 6. Correct. So you view again, you see, is it all connected? See, E, F, B, A, C, D, H, G. Surprisingly come out so nicely. So nicely. So in that case, you need to further do 2 more job only. Link depot to E and link G back to depot, or either one. Okay, either your depot to G, then E back to the depot. You complete one vehicle nicely. Sui sui. And this is optimum. Optimum? No, no, no. This is near optimum. Okay, it may be it may come another algorithm which is more optimal, but this is actually better than just now. These greedy, but it may not be better than DP, but somehow it should be near to DP lah. I guess this one could be very near optimal already. Okay, right. Now, how about the other side? You do the same for the other side. Okay, so again, okay. uh, you calculate all the tables. So you start from I and J, you link first. I and J, you link. Okay. Then, sorry. Then, okay, this I and J is a redundant, kick it out. Then you start with link I and K. So I and K, you link. Then you go J and M, you link. Okay. Then you link, this is loop lah, huh? K and L cannot link, K and L, the link become loop already. So you link L and M. Okay. So you again, you check L, K, I, J, M. Link already. So what you need to do is you just need to link that port to L or that port to M, and then L back to the depot or to the original port. Then again, you get a very nice, okay, very nice link. And the cost is 42. Double check and see. Is it 42? Okay, just now compared to greedy. Greedy, what do we get? 45, right? Greedy. Greedy, we get 45. See, it's better. Huh? Heuristic is better. Okay. I would say it's optimum, but I'll say it should be near optimum. Okay. Okay, right. Now, if you continue this method you do for 3 vehicles, what do you get? You get 46. You get 46. So better than the greedy. Greedy just now 3 vehicle is 51, right? 51. See? So this actually proves that heuristic will better than greedy. Okay, we're better than greedy this case. Okay, but surprisingly, the third vehicle may not have much function. You see, let's say assume that yellow is vehicle one, green is vehicle two, so vehicle three just pick up L and then come back already. Because again, your goal is try to hit the total minimum. If you let the third vehicle go many rounds, your return path actually is costly also. That actually will shoot up this number where you don't want. So in that case, if you based on this algorithm, you calculate that actually the third vehicle just pick up L and then come back. Okay, right. So your second vehicle actually is you don't pick up from L. Your second vehicle actually is go to M. So you pick up L and pick up J, pick up I and K, then just use the L via to go back to the depot. Okay, all right. Ah, so because your requirement is total cost, okay, right? So unless again you change your requirement, where your now requirement actually is, uh, you want to balance all the vehicles should have more or less equal load. That would be different already. Or maybe you cut, okay, maybe vehicle one use too long time, you want shorter time, then your metric will be time already. Or time cost, time cost. It depends what metric that you want. Okay, but anyway, heuristic actually proven that is balance, okay, between those guarantee optimum and also within those fast one. It gives you a balance good solution or near good solution or near optimal solution. Okay, now if I go a bit nasty, okay, now the path I change, a few paths I change. This is 4, I make it 7. This link is 3, I make it double 6. And this is 8, I make it 1. I make it 1. Okay, now I use heuristic again. What will be my answer? You curious want to find out? Or you want to try? Give you 2 minutes. It cannot be too long. You try again. What kind of topology that you will get? Okay, right. So let me show you. what I managed to calculate. Ah, EFB. Okay, all right. Interesting. Okay, we discuss, huh? So you'll be very surprised that your total cost slightly lesser, 41, if you use heuristic. Okay. So, but again, you see, now vehicle one have to go super long path. Okay, right, super long path. And vehicle two, not much function one. You just pick up G and come back. Okay. So because this path is uh very short, one instead of 8 units, now 8 units, 1 unit. So actually the algorithm will calculate that total minimum. Better let vehicle one to cover as much as you could. Okay, the cost actually is much lesser. But again, it depends on your question. If your question have other metric like time constraint, or maybe the vehicle cannot go too far, or maybe the vehicle, the storage is limited, cannot store so many parcel. So in that case, you may have to force to chop somewhere and go back to depot, let the vehicle two to cover. Okay, now you'll be very surprised, even I use three vehicle, doesn't improve much. Okay, right? It doesn't help much. So vehicle one will still cover a lot. Okay, until the you go round until the I then come back already. So it will let vehicle two to cover the G and cover the L. Okay, right? Because again, your goal is to hit total this cost. Huh? Right. So there are few important factors lah. First is depends your distance. For your hackathon, you need to consider how much parcel you can pick up. And then you still have I mean you still have what you need to consider what Monday, Tuesday, Wednesday, Thursday, Friday, okay? Right? And you may need to consider the length. So that actually complicates the problem. But anyway, once you master the algorithm, okay, you can use those algorithm to find. Okay, of course, the condition you must cover all the point. You cannot say, this not so far away, I don't want to cover. Then immediately you fail already. Okay, we'll kick out your proposal. No choice, lah, huh? Right. So all nodes must cover. This is the first condition. Second is how will be the these are optimum. That's why you have two proposals. One proposal is maybe you can use brute force, okay, to calculate. Okay. Or maybe use greedy to calculate. Greedy lah. Better lah. First you use greedy. Then second one you may use slightly better one to calculate. Also can. We want to see a comparison or improvement of proposal lah. This is a requirement. Okay, can Right. Now, when VRP actually is many to many. Okay, that's why but you cannot, I can't straight away talk about if you are beginner, I can't straight away talk about VRP because you were lost. So that's why I give you the idea how we get minimum path or shortest path. Then from there, how we from minimum path, how we enhance become TSP, travel salesman problem. Then from there, only we talk about vehicle routing problem, VRP. Okay, so I hope you get the full concept rather than you blindly throw all the data into the AI and don't know what is the outcome. Okay, right? Okay, and there could be a lot of false data you also don't know, or false outcome that you don't know. Okay, so at least now you have idea how to verify, even you use AI, or even you can prompt much better to specifically ask the AI to use what particular algorithm or particular field that required by this hackathon question. Okay, right. Now, be very careful when you play with routing because you may face these four common problems or maybe others lah. The first is sometimes you may simulate a way, okay, until that you have this route poisoning. We call it link failure or route failure or route unreachable. That means suddenly the node disappear. Or suddenly the link broken. It can happen one. Can happen one. All right. So in that case, you may need to reroute. Okay. Or maybe it's a bug. Okay. So you better check. Okay. If you have unreachable nodes, if it's a bug, then it's a big problem. So you need to check. This may happen one. You may have poison reverse. That means suddenly somehow A go to B and the B will go to A go to B again, B go to A again, then forever is ding ding dong dong there. This is reverse arrow. Okay. That is very killing one. Okay. Then you may have a loop, like what I say, you may go to A, go to B, then go to C, C go to A again. Then you play a loop. Okay. Or sometimes maybe your topology go huge. You are not aware actually it come back to a loop. and then your vehicle will go in a loop again, and loop again, go round and round, 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 round. Ha. Then you cannot come up. Okay, that can happen now, huh? The other one is asymmetric. I'm not sure whether this will happen at your hackathon question. That A go to B, the cost is 5. B go back to A, the cost may not be 5, maybe 8, or maybe something else. We call it asymmetric routing. Okay, right? So A and B not equal to B to A cost. It depends your question requirement. Okay, so just take note of these items. All right. So I hope that when you start to do those questions, you must have certain awareness lah. Huh? Of course, I do hope that during the hackathon presentation, okay, you can highlight or a proof that how you get those number rather than just say AI give me this number. Okay, you need to prove to us how you sure that this number is optimum or is a near optimum or maybe not near optimum. Okay, but at least fast enough to get some outcome. Okay, you need to explain those figures or not just telling the judge, oh, these are the figures. How do I know whether this is valid or not valid number? Or at least now you have a base, okay, to verify those numbers. Okay, right. I cover until here, so thank you so much. My next colleague, Miss Tan, she will continue to guide us, I mean, all the students to about simulation. That means how to have a UI to see all those notes or your lorries going around. Okay, yeah, that's all. Thank you. Yeah, pass to you, Mr. Yo.
Okay. How about we take a break for 5 minutes?
Uh,
Uh,
yeah, I suggest maybe for my side about the theory part because Miss Tan will cover the simulation part. So for my
yeah.
part, if maybe I think some question first. If there's a
Okay,
question from the students,
can. Yeah.
any
So
question from students? Confused already.
burn out if you burn out.
Okay, yeah, no question. Yeah, I think no question. Okay, anyway, if no question, then yeah, I think like what Mr. Yu suggests, maybe we have a 5 minutes break and then we come back, then Miss Tan will continue. Okay?
Okay.
Okay, right. Thank
Thank
you.
you, Dr. Go. We come back 10:37. Teacher Tan, can you share the slide, see whether you got permission to share?
Hello,
Hi.
okay. Good morning.
Morning. Okay, can. Okay. Then we just wait until 10:37.
Okay, no problem.
Okay. So now I pass the mic to Teacher Tan.
Thank you, Mr.
Okay.
Yo. Eh, Did I share my screen?
Yes.
Yes, currently sharing. Okay, thank you, thank you. Good morning, everyone. My name is Tan Lei Yin. You can address me as Miss Tan, and I will be handling the part 2 of the vehicle routing protocol. Today, I will show you a simplified version of TSP or VRP, okay? If you have any questions, feel free to type in the chat. Logistic optimization is the process of transforming the raw data such as locations and coordinates, and then into actionable delivery decisions. After that, we will actually move on step by step. We are moving from the data, which you can download from the Hackathon official website. We will convert the data into the distance calculations. After that, we will move on to the route optimizations, and finally, we will move towards the simulation and evaluation to evaluate how effective is the route after you have optimized it. And this represents a simplified version of the real-world logistic problem, where multiple depots must serve multiple customers. In practice, companies must determine not only the sequence of the delivery, but also how to balance the constraints such as cost, time, and demand fulfillment. And this is one of your requirements for the hackathon question. Now, imagine you are managing delivery trucks and you have multiple depots and multiple customers across Malaysia. The question is, in what order you should visit them? What route is the best? How do we measure best? And we also need to consider the real-world factors such as delivery time, transportation costs, and customer demand. When we talk about from one route to another route, then you might be thinking, why we not just use Google Maps? The Google Map is very useful because he have a live traffic. Like if now I want to drive to Seremban, I put into the Google Map always. He can help me to calculate the ETA is how is the duration like the ETA. And it also can show me like if I'm using the toll path, then what is the cost of the toll? If I'm using the path without a toll, right, then how long will it take, and etc. So, but the Google Map and Waze, they can't handle 100 customer. Or in your hackathon question, you have a lot of customer. If not mistaken, it's around 40 or 50. And Google Map cannot help us to handle this amount of the customer. They also cannot help us to calculate and minimize the overall cost. Because Google Map is just following our instruction. We are telling them from point A, I want to visit point C, and point D, point E, right? He only can show us the total amount of time that we are going to take, but he won't be able to help us to calculate the cost like the petrol cost and etc. So the tool like Google Map actually can provide us a route between locations, but they are not designed to optimize across many possible combinations. And they also cannot help us to build out a route with business constraint. And this is what we are going to do for our hackathon question. In the real logistic planning, right, we must consider additional factors such as delivery schedule, vehicle types, and operational costs. And Google Map always can't do all of this for us. The problem that we are going to solve belongs to an optimization problem known as the Vehicle Routing Protocol or VRP. It actually extends the traveling salesman problem by considering multiple vehicles and real-world constraints. So just now, Dr. Go already showed us about TSP, and he did mention that VRP is very complicated. And yes, in your hackathon question, we have 3 types of vehicle. And when we have multiple vehicle, we have multiple depot, we have multiple customer, then eventually we may come into the vehicle routing problem. And our objective is to serve all the customer and return back to the depot while minimizing the overall cost. When we come into the organizations or a business, right, all the things that the boss is focusing is the cost. We want to achieve our objective with a minimum cost so that we can earn more money and save the environment to maintain a green environment during our transportation. The fundamental of TSP and VRP were already covered by Dr. Goh earlier, so I will not go into the detail, but instead, I will show you how exactly we can do that. So our approach, this is a big picture. Our workflow consists of 4 main steps. First, we convert the geographical coordinates into distant metric that computer can process. Because all of the data currently are in CSV file, right? We are going to extract out the information that we need and put it into our programming. The second item that we are going to do is in here, I will be going to use genetic algorithm to search for a good delivery route. We noted that this is a good delivery route means that it may not be the best, but after a lot of interaction or a lot of generation, right, then I get the best among so many of them. Okay, so I will be using genetic algorithm for that. And third, we will simulate the performance of the route generated by the genetic algorithm. And we want to measure the performance by using some important indicator, like for example, fuel consumption, time taken, and the cost that will be consumed. And finally, we will visualize the route to better understand the solution makes sense or not. Okay, so what is genetic algorithm? You can think that genetic algorithm as one of the survival of the fitness process of the solution. Instead of checking every possible route, we are allowed good solution to evolve over time. Like just now, Dr. Goh already shows you by showing you several position or coordinates, then ask you to find out the shortest path or the lowest cost path, right? Genetic algorithm also can do that, but the solution provided by him may not be the shortest path, but it is a good solution. Like for example, I have multiple points, then based on the factorial calculation that shown by Dr. Goh, you know that when come into 20 or 30 numbers, right, the possible routes it will be increasing. So in that case, we don't want the algorithm to compute each of the path, but we keep on let it to randomize some path. And let's say I let it to randomize for 200 paths. Among the 200 paths, I will select the best one and my algorithm will end over there. So it won't really consume much time for my algorithm to explore each of the possible paths or when can meet all of the coordinates, like meeting all of the customer and etc. Genetic algorithm, you can set it stop at 20 or 200 or even 5,000 possible solution. Then among these 5,000, I select the best and I will stop there. Okay, so in genetic algorithm, how do we start? We will start with a new generation, which is a set of randomly generated routes. And then we will perform a fitness evaluation. Each randomly generated route is evaluated using the fitness score. And in our case, right, the example that I will show you later, right, the fitness score will be the shortest distance. But in your hackathon, your fitness score will not only the shortest distance. You should be setting the lowest cost. After we evaluate each of the individual, right, we come into the selection. The better routes will have the higher chance being selected as a parent. But the weaker one will still be maintained in the history because we want to maintain the diversity. After we select the better routes, right, we will perform the reproduction, which include the crossover and mutation. In here, let's say we have two parents, and the remaining coordinate are the child. And based on the parent, we will actually doing the crossover and mutation to form the full routes, to complete the full routes. After that, basically what we are doing in crossover is we take two parent routes and combine part of them to create a new routes, and then inserting some child inside and complete the full routes. After we get the full routes, then we will go back to evaluation. Well, mutation is we are swapping two locations, meaning that from A to B to C to D to E. I already have this position or sequence. So I swap two locations among each other, like I swap between B and C, and I calculate the fitness score again. So by doing so, right, I'm able to explore the new possibility. Maybe after I swap, I get a better result, right? And this whole process will repeat over many generations and depends on how many generations we have set. You can set to 200, 1000, 2000, doesn't matter. Okay. Over the time, weaker solution will be eliminated and the population gradually converge into a high quality or near optimal routes. Then we will get the route that we want to use. And genetic algorithm is for us to optimize only, not yet simulate. It is important to distinguish between optimization and simulation. Optimization will focus on finding a good solution based on the defined objective, such as minimizing distance, lowest cost, and etc. While simulation, on the other hand, he will evaluate how the solution perform under more realistic condition, like the route generated by optimization. I will put into the simulation tools, or I will simulate the routes by considering the cost, the time, or the fuel consumption. Then I will get a report. Then the report generated will help us to evaluate how effective is the route generated by the optimization. And in this workshop, we are going to use genetic algorithm for optimization because it's quite fast. While we'll use a Python-based model for the simulation because it is very simple. We noted that the genetic algorithm that I'm going to show you later is just one of the example. Like what have been discussing by Dr. Go earlier, you have a lot of optimization algorithm you can use like brute force, nearest neighbor, and the SCO also can, and whatsoever. Okay. While simulations also have a lot of simulation tools you can use. The simplest is I'm using Python. The less technical one is XL, which is covered by Dr. Dio yesterday. You also can use any logic. You also can use Sumo. Sumo is a traffic simulation tool. You have a GUI, you need to do some configuration, then you can see how does the traffic looks like and etc. You also can use MATLAB, you also can use OMNet++. There's a lot of simulation tools you can use. You can discuss with your coach later and see which one they recommend to you, okay? So what we are going to see today, in these sections, we will go through four main steps. The first step is to build a distance metric, then apply a genetic algorithm to find a route. After that, evaluate the key performer like the cost, fuel, and time. And finally, I also will visualize the route optimized by GA. Okay, so we will be using a simplified data set for the demonstration. The hackathon question required additional consideration, but in here, I only will show you the simplified version. Okay, so the simplified version of the data set that I am using, let me show you. I already extract out only certain customer, their latitude and longitude, which is their coordinate, their positions are basically, and I only put one depot. So what I'm going to do is I will ask genetic algorithm to generate a path, a good enough path for me. The vehicle will visit from the depot, visiting all of the customer and return back to the depot. Okay, so this is what my genetic algorithm will do. And this is my code. Can you see the words, or is it the front is too small?
The front is too small.
Is it?
Yeah, maybe need to be bigger a bit.
Yeah, so let me make it 20, is it enough? Maybe 26. Okay. 26. Like this is better?
Yeah, better.
Better, right? Okay, thank you. So I separated into multiple Python file because I want to show you the 4 step, right? So that's why I separate into 4 Python files. But for you, you can actually combine everything within the single Python file. So what I'm doing for the first Python file is I read the process data that I showed you earlier, which consists of the customer or the depot ID, then their coordinates, which is the latitude and longitude. After that, later I will come to this function. After that, what I do is I put everything into the data frame, and then I will start a loop to calculate the distance between each of the position. Meaning that, let's say from depot to C002, what is the distance? If I want to drive to this location, right, how long will it take? Then I will calculate again from depot to C011. How long does it take? What is the distance? Then I calculate again depot to C013. Then depot to C014 until visiting all the customer, right? Then from the C002, I will calculate from Z002 to depot. Then I calculate 002 to 11, 2 to 13, 2 to 14, 2 to 18. So I calculate all of them before I feed into the genetic algorithm. Okay, so that's why I use a for loop inside. And this get distance function is the one that helped me to get the exact distance and the time, the driver time. Okay, so in this function, what I do is I send 2 coordinate, right? After that, I call API. I'm using the open source routing machine. It is an open source route planning library for driving on network services. Okay. Basically, this is one of the free API that I can find from the internet, and the internet have a lot of other possible API that you can call to help you to get the distance. Okay, so after I get the distance, right, this is the distance, and this is the hours. Okay, so I will store them into my another 2 CSV file because I'm going to export it from here and import it into my genetic algorithm. If we are using the same Python file, then no need to be so troublesome. You straight away can reuse the variable and parameter already. So how does the CSV looks like after I ask him to calculate? So this is it. From depot to C002, the distance will be 279.34 km. If I drive from depot to C11, I will get this distance. Then from depot to C13, I will get this distance. So I form this table already. I will fit into the genetic algorithm. This is the distance. I also have another one, which is time metric. This is the time taken for them to drive. So the distance metric and the time metric in here, right, is not something that you can straight away use the mathematic equation to calculate. If you calculate in mathematics, if you calculate x1, y1 to x2, y2, you are drawing a straight line. But in reality, especially like we are using Google Map or Waze, you have some traffic condition. You have traffic lights. Some of the path you can drive, you need to U-turn, you need to go into the roundabout and etc. So two positions are not a straight line to connect between both of them. They are not a straight line. That's the reason why I'm using this API, because this API basically is using the map to help me to do the distance calculation and to help me to retrieve how long does it take when I want to drive from one position to another position. Okay, be noted about that. You cannot straight away use the x1 minus x2 then plus y1 minus y2 and etc. square root or whatsoever. You cannot do that. So you must use API to help you to get the distance. Okay. After I got the total distance, which total distance and the time, right? The next one is genetic algorithm, which I import into my GA. So I import inside my genetic algorithm, right? I put them into the list and I define some global parameter. The top three are the parameter that used by the genetic algorithm. Pop size is indicating how many coordinates I want him to go to. Generation is the one that I told you just now. He will run 200 times. He will perform the route for 1,000 times or 5,000 times and etc. So this one also depends on your configuration in here. Mutation rate is the random parameter that you want to mutate between two positions. Let's say A, B, C, D, E, F, G, right? I want to mutate B and C, make it become A, C, B, E, D, E, F, G, something like that. So what is the mutation rate? I'm using a 0.2. When you are working on your project, and if you are using genetic algorithm, you also can modify this value and see what is the effect. Okay. The following four parameters are the one that I use for the simulation. I know about the fill rate, their price, the fixed cost, and then the maintenance, etc. In your hackathon questions, the parameter already given to you. You can take this out, and when doing simulation, you can put it inside. This is the fitness function to calculate the distance. We have the time function as well to calculate the total time. And the following few functions are for genetic algorithm. We will first create the population. So this one will return a population that are randomly created by the genetic algorithm. Based on the randomly generated population, I will do the selection. And then I will perform the crossover by identifying two parents. The child I will append at the end of the routes until a complete route is generated. After that, I will perform a mutation, meaning that I randomly swap between two positions and calculate the routes again. While the simulation is the last part, I will calculate the total cost, total time, fuel use, and the total cost. This is the genetic algorithm that I'm using. First of all, he will call the create population to create a random population first. After that, he will start the loop. In this loop, he will extend the created population. Then he will select the parents among the population. After that, he will cross over the parents to append the child to complete the routes. After that, he will mutate the child, meaning that he will swap position randomly among the generated routes. Then he will get a new population. After that, he will track which is the best. he will track among this route, among this process, right? Among this route, which one is the best? And then he append into the history. And finally, he's picking the best generated routes, the lowest cost in here. He will generate it, and then he will return back to the main function. So the Python code will first run the genetic algorithm. The genetic algorithm will run each of the functions separately, right? And I get the best route, best distance, and history already. So I can form my full routes. And then I will run the simulation to simulate the total distance, the time taken, the full, and the cost. And finally, I will print out the simulated result. So the simulated result is, okay, so this part is the one that I run my genetic algorithm. The bottom part, I don't know how to make the text bigger. Setting again. Common links. Okay, so when I run my genetic algorithm, you can see that starting from the zero generation, the initial path that he calculate for me, the best distance is this amount. After that, he will do the first generation, second generation that I didn't show in here lah. I only print out every 5 generation because I print out all the 200, it will be super long already. Okay, so after a while, you can see that you can see that when come to 20 generation and the remaining, although he keep on performing crossover and mutation and generate a new path, but you can see that the distance not being replaced, meaning that maybe at around 20 generation, I already get the best path, but he won't stop. The program will not stop. He will continue until the 200. This is the 195 that should have a 200, but I didn't print out because upon reaching 200, I already get the best result. So if I start from the depot, and at the depot, I follow this sequence. My total distance travel will be this. Total time taken is this. The full use is this. And the total cost is this. After that, I save into my another CSV. Okay, so this is the optimization. Best route is from the optimization. While the bottom, the total distance, total time, flow, use, and total cost are from the simulation. But sometimes the simulation that I'm using here is quite simple, but sometimes I want to make it more detailed. So I have another simulation Python file that help me to do the similar stuff. Just that on top of that, I asked him to calculate the distance between two nodes and the time taken between two nodes. Because the simplified simulation that I did in the genetic algorithm Python file is a total cost. If I want to see from point A to point B, he will take what is the distance, what is the cost. Then from point B to point C, what is the distance, what is the cost. So I want to see that detail, right? I can do it by using Python as well. So these are the detail. From depot to the first customer, total distance taken is this. Total time taken is this. From this one to this one, distance is this, time is this. So you may ask, why this is so important? Why I want to see all of the details? This is important because algorithm only help us to select the good enough path or best path. But he did not consider the driver situation and traffic condition. When generating or when optimizing a path, you can put that into your requirement. But just now what I doing, right? I didn't consider those situation. So you cannot say that, okay, the driver from depot go to here already, right? Then 3.34 hours, then straight away start and go to C14. He need rest. He need time to eat his lunch. He also need time to sleep and etc. So that's why I asked him to list out in detail, and from here I can identify where is the problem and fine-tune my algorithm. So this is also possible. And of course, at the end, I will add a total distance and total time and fuel use and total cost lah. Okay. And now we only seeing the values, the numeric and the calculation result, right? What if I want to visualize the route? So it is possible. For route visualization, I look in back the raw data, the one that before genetic algorithm process it, I retrieve all of the latitude and longitude. After that, I also read the best route optimized by genetic algorithm. I put them into the list. After that, right, I creating the map. I'm using a volume. Volume is a map API that can be called in Python. And each of the position, each of the location, right, I add a marker on them. After that, I create a HTML document. And then I draw the routes to link between two positions, from position A to B, and then from position B to C, and then from position C to D. I use a polyline, a very simple one, and I save to the route.html. So how does it look like? It will look like this. So from here, you can see that I'm starting from one depot. He will go to Georgetown first. The one is in Georgetown. After that, he will go to Alaska. Then he will move down. Instead of Kuala Lumpur, he will come to the Selangor first, and then Shah Alam and etc. Then he go down to Seremban. And after that, he will straight away go to Johor Bahru first without visiting Batu Pahat first. Okay, he go to Johor Bahru first, then go to Batu Pahat. After that, he return to Kuala Lumpur and he return back to the depot. Then you may ask, why he come to the Selangor already? Why he doesn't want to visit Kuala Lumpur first before going down? This is the path that generated by genetic algorithm. He performed 200 interaction and figure out that this is the best path. Of course, you can arrange the route by yourself and simulate the routes, get the result like total distance taken and etc. Then compare with the one that genetic algorithm generated for you, and see what is the difference. Because your hackathon question, you need to write two proposals, right? So you may consider to use this technique. So this is a path generated by genetic algorithm, but this visualization is not so good because of I'm drawing a polyline between two positions, and it is not driving, like it is not using the route on the map. If you want to use the route on the map, right, it is also possible. We need a additional API. So the additional API, I'm doing the same thing, just that the additional API I'm using is again OSRM. OSRM also can help us to understand the route condition and etc. and help us to draw the driving path. Okay, so when basically the rest are the same, like creating map and then add marker and etc. But when I drawing the routes, instead of using the polyline directly, right, I will go into the loop, reading from the first position to the next position. And then I will call the OSRM to help me to do the segment. After that, I will draw out the segment. If my API fail, then I use back the traditional line. If the API works well, then I will use the segment to draw the polyline instead. So how will it looks like? It will looks like this. So you can see that when from this farm or depot, he want to go to Georgetown, he will go to the top one, then drive into the Georgetown, then from Georgetown go out to Alostar, then from Alostar he will go down and etc. Even you can also zoom into it and see the condition. You see like over here traffic light, then over here roundabout maybe it's a flyover because KL and Selangor have a lot of flyovers. Then you have a roundabout and etc. So he will show you the detail. And this is our visualization. And so far what I have done, I'm only using algorithm, meaning that I'm using Python only and calling some API. If you want, you can use some other simulation tools to help you to simulate the path generated or suggested by your AI model. Okay. So you may ask, because I'm showing you genetic algorithm, so is genetic algorithm an AI? And the answer is yes, genetic algorithm are part of AI because AI is something that he will learn and then he will make decisions. So this genetic algorithm also same, he will learn from the history and then keep on generating the path and then select the good enough one and make decisions about which one is the best. Okay, so it is a evaluationary AI or the optimization technique that usually used by us. It is different from the learning-based AI like deep learning and etc. It's different, but it is still part of the AI. Then come back to another question that raised by Dr. Go earlier. If a route is the shortest route, is it always the better one? The answer is no. The shortest path doesn't mean that is the best path because in your hackathon problem, you need to satisfy a lot of constraint and requirement. For example, if you download your data set, right? You have a lot of separated CSV file, or there is one CSV that contain everything, basically are the similar, right? So the customer also have their own constraint. Like if you open up your constraint, you will have your delivery window, your maximum lead time, and etc. So this is the customer constraint. Then the farm also have their own constraint. The farm constraint is like available day for you to pick up the vegetable or fruits from them, and they also have daily capacity. And both farm and customer also have their location constraint. Their location are different. So some farm are in the middle of Malaysia, some of them are at the bottom. Then some of the customer is at the top. Then some of the